Hi, thanks for giving me the opportunity to present my work and the work of my collaborators here. It's nice to be back. As Ian said, I will present some work that we have done in order to estimate the disk mass of protoplanetary disks, and also some more work that we have done using Phantom to benchmark this model. So first of all, why the disk mass is important? Why do we care? For many reasons. The first one is that depending on the disk mass, we will end up with different type of exoplanet, different distribution of exoplanets. So it's important to know how disks are massive. Then the disk mass is important because it enters in the dust and gas evolution process. So depending on the disk mass, we can have more coupled dust and gas. So we can have different substructure, so different processes involved in disks. Then it's important in planet evolution because depending on the disk mass, we can have different migration, different accretion, so different types of planets also. So in general, I would say it's important for the entire disk evolution, and if you want to comprehend better what is happening, we need to understand how massive are these disks. So how we can get the disk mass? We can get the disk mass mainly from, the usual way is to get the disk mass from the dust. So with the assumption that the dust is optically thin, we can get an estimate of the dust mass. But then there is a large uncertainty on the opacity and also on the composition of the dust. And if we want to convert the dust mass into the total disk mass, we need to know a dust to gas ratio, which is also a very uncertain parameter. We can also look directly at the gas, but then this is even more tricky because the main component of the gas is the molecular hydrogen, which is we are not able to detect it. So we have to search for other traces such as CO-isotopologues. But then here, by looking at estimates that have been done by looking at CO-isotopologues, we can see that we are actually able to just infer a lower limit for the disk mass. And this is because we are not sure about the parameter, the convection factor between the CO-isotopologues and the molecular hydrogen. So this is another factor of uncertainty. And also, I would say we have also to take into account that gas and dust have different evolution, so we can end up with a very different distribution, density distribution for the gas and for dust. So the dust usually settled onto the midplane. It's very compact, while the gas is more expanded and fluffy, so we need to take into account that we have a lot of uncertainty in concerning the disk mass, and so we need to search for other ways that might be independent of the conversion factor between the CO or dust to molecular hydrogen. So the first thing could be that we can look at the HD measurements. The only issue is that we don't have a large sample of HD measurements in disks, but this is actually promising because for the system where this has been done, the disk mass estimate was that we got was actually higher, was actually larger with respect to the CO isotopologue. Then we can also look at different dust lines at different wavelengths, and so this can give us a total gas surface density estimate. And we can also compare substructure observed at different wavelengths, for example, a scattered light and in a continuum, and from this we can get a local estimate for the surface density. But actually, there is another way that it was not used in our community, but in other community, which is to dynamically search for self-gravity deviation from the Keplerian rotation curve of the disk. But before going to the point, I would like to tell you a bit before. Sal already described a little bit why self-gravity is important, and when the disks are self-gravitating unstable. So we can derive the tumor parameter that Sal introduced before from the Lin-Shu dispersion relation. And when the tumor parameter is approximately equal to 1 or less, we can say that this is self-gravitating unstable, meaning that the disk self-gravity wins the gas pressure and the rotation. And so why self-gravity is fundamental to understand the entire process of planet formation? Because we do expect disks to be massive, especially at the initial evolutionary stages, after or like during or just after the formation from the parental molecular cloud. And also self-gravity can enter in the process in a later stage when there is infall from the molecular cloud or there is rapid accretion. So we can end up with like the formation of a companion or like of planets. Then, especially for the formation of planets, as Sal already described in his talk, and also as Cristiano will present his work in his talk tomorrow, we can have that dust can concentrate in the spiral arms, and this can actually help can help for the formation of planets through direct gravitational collapse. Also I would say we can, it would be interesting, and it's something I would like to do at some point, soon, to investigate how this change, if you consider also dust growth in the picture. Then another important question that we need to ask ourselves is if planets are forming early in the disks, what happens to them? I mean, are they able to survive in such an environment or not? And there were some studies that have been done. For example, Clément Baruteau found out that it was unlikely for them to survive, while instead the Sal, in another study, like with a different assumption for what regard the beta cooling, he found that it's actually possible for planets to survive. Then another important point, especially for the work that I'm going to present later, is that self-gravity contributes to the gravitational potential in two ways. So there is a basic state, which we can get by looking at the supercapillarianity with respect of the rotation curve, and then there is non-axisymmetric perturbation, which are like the spirals, and we can see that like spirals in density corresponds to the so-called GI wiggle, which are like kinematics perturbation, which also Cristiano will present in his talk tomorrow. So let's go back to the dynamical scale idea. So the idea is that usually when we want to, when we consider protoplanetary disks, we assume that their mass is actually much less than the star mass, but there are some cases in which this is not true. So the disk contribution to the gravitational potential is actually important. And so in this case, we can describe the rotation curve with three different terms. There is the first term, which is the star contribution, which is the Keplerian term. Then there is the disk contribution, which is a super-Keplerian term. And then there is the pressure contribution, and we have to consider both the radial and the vertical direction. This is actually further development with respect to what we have done in our previous work in 2021, where we consider just the radial dependent of the pressure gradients. So by putting all these terms together, we can see that we can write the disk rotation curve as a sum of a Keplerian term and two sub-Keplerian terms and the super-Keplerian terms, where the two sub-Keplerian terms are due to the radial pressure gradient and to the vertical pressure gradient plus the star contribution. And when the disk contribution is not negligible, when the disk is gravitationally marginally stable, but we can also find a set of parameters for which the disk is actually gravitationally stable, but its contribution to the gravitational potential is important. This, as I mentioned before, is something that people in the galaxy community usually do, and also it was done by Giuseppe Lodato and Bertin in 2003 to measure the disk mass of an active galactic nuclei. And through this method, we can actually infer three quantities directly. We can infer the star mass, the disk mass, and also the outer disk radius. So the first candidate to which we applied this model was LISO 27, which is is very well known in our community. It has two very nice large-scale spiral structure, and it's from the literature. The disk to star ratio is 0.3, which is telling us that the possible origin for the spiral arms is actually GI. So Teresa Paneque Carreño analyzed new data now like few years ago. And we, for us, it's particularly interesting to look at the gases. So here there are two moment zero maps for the 13CO and C18O isotopologues. An interesting thing to see is that especially for the 13CO, but also for the C18O, we have an asymmetry between the east and the west side, meaning that the east side is much more extended and cloud contaminated with respect to the west side. This might be due to inflow. This is something that still needs to be understood. Then from the kinematics data, Teresa derived the disk rotation curve, and she actually fitted these curves just with the Keplerian model. What we actually did was to consider our self-gravitating model that I described before, and two Keplerian model, one with the star mass, and one with the star mass obtained through the self-gravitating model. And we can, here I'm just presenting one of our results. It's a bit blurry, I'm sorry, but yeah. One of our results, because we actually performed different analysis by considering at the same time and individually both CO-isotopologues and both sides of the disk. And here we can see that the two models actually differ one from each other quite well, and we can see that the best fit is actually the self-gravitating model, and the self-gravitating model is the black line, and it goes from the Keplerian model, where the star mass has been obtained through the self-gravitating model, to and in the outer region it flattens and it's overcome also the Keplerian model. So we can actually see that this model is actually reproducing well our data. Then last year, Giuseppe Lodato and many other collaborators performed the same analysis on two other disks, IM Loop and GM Auriga. And especially for IM Loop, they found that the self-gravitating model was actually fitting in a good way the data, and what they obtained was like a disk to star mass ratio of 0.1, meaning also in this case that the sparks that are observed could be due to a GI. They can also be due to an embedded planet. I mean, we will not know, I don't know, yeah. But this was also a nice result. What we are doing now is actually to test this dynamical scale with the self-gravitating disk simulation. So in order to benchmark our model, we are, me and Cristiano have performed different self-gravity simulation with Phantom and then with MCFOST, with both cooling on and no. So meaning that the disk is always self-gravitating unstable, but we can, in this way, we can we can consider disks where the disk is gravitationally unstable, but also disks where the disk is massive but not gravitationally unstable. Here, as a first test, I'm showing we have performed the first test by looking at obtaining the disk rotation curves directly from the hydro simulation at the midplane, and from this plot we can see already that increasing the disk mass as expected, the velocity increase, and going further with respect to this dotted line, which corresponds to the model where only the star and the pressure gradients are considered. And by fitting these curves with our model, we're actually able to recover the disk mass that we know are in our simulation. The disk mass, the star mass, and also mostly the outer radius. Here I'm just showing the main parameters that we use for our Phantom and MCFOST simulation. So these are the disk masses that we used in our simulation, and also we perform different simulation for considering two isotopologues, 12CO and 13CO, different line transition, different disk inclination, and also different spectral and spatial resolution, because what we actually want to investigate, we want to benchmark our model, but we want also to understand what is the minimum disk mass that we can measure with this method, and how the spectral and spatial resolution affect this measure. For the test case that I'm presenting, the result that I will present later, I'm considering the 2-to-1 transition line, the 13CO, and the inclination of 30 degrees, and this spatial and spectral resolution, which are the same of the map surveys. So our workflow is from the synthetic, from like the MCFOST simulation, we extract the emitting layer with disk surf, which is a tool from Richard Tigg. And in this case, we assumed an exponentially tapered power law, and here we can see the different, like just as just an example, we can see the different emitting layers for different disk masses, and also in this case, we go from like the lower disk mass to the higher disk mass. Then, with knowing the emitting layer, we can actually extract the rotation curves with EDDI, which is another tool of Richard Tigg. And here I'm just showing the rotation curves that we obtain for a specific disk aspect ratio at 100 U of 0.07. And also in this case, we can see that what we expect to see, so like increasing the disk mass, the velocity increase. For the errors, we considered uncertainties on the emitting layer, which is using the 16th and the 84th percentiles. This. And then what we finally do is to fit the curves that we obtain with our model with an MC. The code is actually available thanks to also Cristiano. And here I'm showing just like a very preliminary results. So in this case, this is for the 13th CO, non-cooling case. And here we are considering a model where we consider the star, the self-gravitating disk, and the pressure gradient. And we can see that we have done this for all the disk masses that we have. And we can see that we can actually recover our disk mass for the 0.05, 0.1, and 0.15 solar masses cases. So we can say, I think we need to understand a little bit more if this is true in every case, but like in this case, the threshold, our threshold for the disk mass, for the minimum disk mass that we can detect is this one. And we have some issue for the 0.2 masses case. But this, I think we understood why, because like if you compare these two plots, so this is like the vertical distribution of particles with respect to the radius, and the orange line is the emitting layer. And we can see that while for the low mass case, the emitting layer is well embedded in the disk. In the high mass case, the emitting layer is not. This is not the case. So we are in a low resolution region, and so this might cause the fact that we are not able to recover our disk mass. And this is actually something that can also affect our simulation with cooling on, so with GI. But this is something that we still need to investigate better. So, like take-home messages from this first part is that we search for deviation from capillarity in disk rotation for different systems, and we are actually able to get this, especially for LIS27 and IM loop, to disk estimates that confirm the fact that the spirals that we see could be originated by GI. Further investigation are needed, especially to understand the asymmetry that we see in Elias, and also we need to extend the sample that of this analysis, and in particular something we will do for Fico 6 and Abia Auriga. And so now we are benchmarking our model with self-gravitating phantom and MCFOST simulation. The main goal is like to benchmark the model, but also to really understand what is the minimum disk mass that we can recover, and how this change depending on the spectral and spatial resolution, because this can actually help observers to this can create a relation where we tell observers what we would need, like what resolution and what spectral resolution we would need, and so to get this observation. There is lots of work in progress. Also in this case, we will do a combined fit for both isotopologues. We are working on a better treatment for the errors, and other 2 points where we were interested were like to understand how does a planet affect the rotation curve, and also what about the binary. And then I already presented this a little bit on Monday, but we are also investigating about a weird cavity that we see in self-gravitating simulation. This cavity that appears to open in the inner region depends on different parameters, the beta cooling, which means like if the disk is cooling fast enough, the cavity is smaller. If the disk is cooling slowly, it's larger. It depends on the disk to star mass ratio, on the viscosity, resolution, and at the same location of this cavity in the density, we have like an increase in the temperature, and this means that we also have an increase in the vertical scale 8, and the disk is kind of puffed up in the inner region. So just like as a test, I got tackled the switch. I don't care, I love it. I'm joking. But I've tried to perform a simulation by just killing the viscosity. We don't get the cavity. Now I'm actually doing another test like that Dan suggested yesterday. It's ongoing. So I hope before Friday to be able to tell something more. And also we checked, like we performed a timescales argument. So we decided to check how the timescales involved in the heating process of the disk compares between each other. So we have a timescale which is due to the PDV, a timescale which is due to the shock, and a timescale due to cooling. And we find that like the cavity open when the cooling timescale is actually larger than the minimum between the timescale related to the shock and the PDV. So in this region, the cavity like opens. Yeah. Next step is in order to understand why this cavity is forming and what we can do. First step is to understand if this is a numerical or physical issue, or maybe both. Are thermal instability is involved? And also maybe in general, I would say even if we are able to solve this issue, not like doing crazy stuff, it would be nice to improve the cooling treatment that is now used in Phantom. Maybe with opacities, or like with the combination with MCFOST, as we were discussing on Monday. Why do I care so much about this? Because actually we want to be sure that the self-gravitating simulation that we are doing are correct, and we don't see like spurious structure forming like we do now in the inner region. And we want to be sure that this structure do not affect the outer region where spirals forms. And also, if you do care really for the whole disk extent, not only for the outer region, you want to know that the thing that you are like studying is correct. It's not something due to numerical issues or a bad treatment of some processes. And this is actually something I would like to reach at some point, because something that I wanted to start already like since a while is to perform a simulation with Phantom of self-gravitating disks, considering also the dust growth. So kind of like in order to see if we are able to get self-induced dust traps, and in order to, also comparing with what Sal previously described in his talk, to see if we see some differences by including dust growth or not, and to understand if what is the main what is the effect that dominates in this case, is the drag or GI. So I think in order to do this, we really need to be sure that the self-gravitating disk simulation that we are performing are correct and are not affected by spurious issue. And with this I conclude.
I really like the thing you're doing with the testing your dynamical mass measurements with like synthetic observations. So I was actually just wondering about your MCMC results. I don't know if you can go back to that slide.
Yeah.
Because we have the same problem where it seems to find the minimum fine, but then you get these like crazy small error bars.
Yeah.
So it's.
So me and Cristiano are working on this. So by using a different treatment for errors, like including the covariance matrix, we're actually able to get larger error bars.
So do you have a, well the question was, do you have a fix for this? Because we have the same problem.
We are working on the fix. We might have a fix.
Okay, it'd be good to discuss, because I mean, it's quite typical you get this kind of thing out of MCMC where you get these stupid error bars that don't mean anything.
Yeah.
It's really hard because you can see it's finding your right minimum, but you don't know what...
No, sure, I agree. You cannot really say, I agree.
Okay, thank Benedetta.